So this is one of the important topic from practical point of view. You must know this topic, the sampling methods for supervised learning. So can anyone tell me out of you what is supervised learning?
सर इट्स बेसिकली लेवल डेटाबेस को मतलब वो रीड करते हैं या ट्रेन करते हैं उससे रिलेटेड टू एल्गोरिथम एंड ऑल.
Yes. So supervised learning means that we have the labeled data. Labeled means that you have that target value in the Excel sheet if the data is in Excel form, and it means that you can map your fx with y. Okay, so x means the independent variables. Let's say that you have a Excel sheet. I will draw it here. So let's say that you have this Excel sheet, and in this A, B, C are my first three components, which are called X of a data set. This D, let's say this is my Y, the output variable. So these first three variables will help me to get the value of Y, and this Y is my label. So this is what is called supervised learning. We will use this Y component. And if we do not use this Y component, we only want to do the machine learning using the X component, that will be called unsupervised learning, because then we are not having the labels or we are not using the labels. So this is supervised learning. I have already told you why if it y equal to fx. And so when we are training our model, there is a challenge that let's say there are 100 rows, right? 100 or maybe 10,000. So let's say that the data is huge and you have 1 lakh rows. Now you have to do the training. And for that, you need to do something in a way that, I mean, it is not advised that you will use all these 100 rows for your training. What you will do is you will break this 100,000 rows into multiple parts. Let's say that you will be breaking this thing into train and test data set. So what you will do is, let's say the standard practice is 70-30 or 80-20. 80% of the data you will use for training. You will randomly select 80% of rows out of these 100,000, and they will be used for training the model, and 20% of the data set will be used in testing the model. It means that let's say you have, so let's say that it looks like something like this. So you want to, let's say, fit a straight line in here. Now rest of the 20%, when it comes, let's say that new data that comes, rest of the 20%, it is lying somewhere here. So you will be doing your prediction based on this predicted line that you draw, that you have previously got through the machine learning training. You will be using this particular line to do the prediction for these 3 points, which are testing values. And if it is doing the prediction in a correct way or the accuracy is high, then you will say that yes, my model is good, because let's say if your training accuracy was 85%, but your testing is also coming out to be 80 or maybe 78%, something like that, then it is a good thing, because there is not a big gap in it. But let's say that your accuracy for test data set was not 80, instead it was only 50%, then there will be a gap of 35%, and this is called overfitting. Overfitting means that your machine learning model is working good on training, but it is working very poorly on test dataset. So this big gap is called overfitting, and we will be discussing these things. But before that, I want to discuss that there are multiple methods to break the original data into multiple parts. Holdout method, k-fold cross validation method, and bootstrap sampling. So holdout and k-fold we have discussed earlier. Holdout means that you are breaking your data into 70-30 or 80-20, and you are working on it. And overfitting, I have also let you know 2 minutes back only, that when there is a big gap between your training accuracy and test accuracy, then it is called overfitting. And we discussed this in previous lecture also. So holdout was same thing, that you, I mean, earlier you were doing 80-20, but now you are breaking this 80 into two parts, let's say 60/20, where 60 will be your training, 20 will be your validation data set. So it has been shown in this figure, uh, and you can see that in a way we are using this 80 in a good way, because we are training now on 60% of data, and we are taking, let's say this was the final exam, we are taking its pre final exam with this 20%, to to make sure that yes, our model is training good, and if this accuracy is similar to if the gap between these two, training and validation, is low, then it is a good thing, and if it is high, it means that the model is again overfitting, because if your model is not performing well on validation, then it is the model is overfitted, the model has been overtrained. So the concept remains same, and if it is working good on validation, it is very high chance that on test data set also your data will be your accuracy will be high of the model. So I also discussed this k-fold cross validation. It means that I will show it in the diagram, that there are multiple folds in the data set, and it is divided into, let's say, 80/20. So 80% of the data is being used for training in multiple parts. So sub parts have been made. Let's say that 5 parts were there, and you are making one fold, one part out of it, in a circular manner or in an iterative manner as the test data set, and other 80% is being used for the training data set, and it will help you to cross verify that yes, my model is being consistent 5 times. The drawback of this technique was that it was highly computational, and I mean obviously you can say that the result is consistent, but then again your model will take a lot of time. It will need more computational power, as well as the RAM and the GPU, everything, when you're training the model. So this is new. This was the last thing that we kept in the last lecture, and this was left out. So bootstrap sampling. So it uses the technique of simple random sampling with replacement, and it simply means that when you are making some let's see in this figure. So when you are making the samples, let's say that you have this kind of a original sample data set, you are taking multiple points out of it and making multiple sample randomly. Let's say that these values have been uh, I mean, they have been made in a different order, and they have been made different samples out of it. There are multiple samples out of it, and then you are trying to do classification on each sample. So this was the first sample, this was second sample, this was the nth sample. So you are trying to do the classification on each sample after this has been done, and then you will take the voting of all the classifiers. Let's say that you are predicting the gender of a dataset. So based on some points, you were predicting the gender of a person, and two classifiers are saying that it is male, the third one is saying it is female. Obviously through voting you will know that it is male. So this is the basic concept. You have to do the voting in this classification scenario. If it was regression, then you would have taken the average. Let's read that what's written here. So bootstrapping randomly picks data instances from the input dataset with the possibility of the same data instance being multiple. It is being picked multiple times. There is a no fixed rule that you have to skip if something has been picked once. So you can pick the same thing multiple times. This is one of the drawback also. But bootstrap sampling is used in machine learning and sample algorithm. So it is called bagging. This technique is called bagging. The other name is bootstrap aggregating. In simple words, we are trying to do the voting out of it in case of classification, and we are trying to do the average in case of regression. So it helps in avoiding overfitting in a way, because now you are trying to work with the samples and not with the original data set every time. So you are trying to improve the you're trying to get rid of the overfitting, because overfitting happens when you try to uh, remember, or what we say, cram all of the data set at once. So now in bagging, a certain number of equally sized subsets of dataset are extracted with replacement, and then a machine learning algorithm is applied of, I mean, to each of these subsets. So when we say that we will be implementing the classification on the samples, multiple samples, it means that these are different machine learning algorithms, and these multiple algorithms can be applied depending upon the dataset type and everything. Maybe if you want to try multiple machine learning algorithms, you may want to do the comparison in the end to make sure that you are making the right choice. So this topic was this much only. We have discussed three things: that for training a supervised model, you can what we say, sample your data into three types of methods. First one was holdout, in which we were uh, breaking our data set into training and testing. And then the second one was k-fold, in which we were trying to train our model multiple times. And the third method was bootstrap sampling, and in this we were simply making multiple samples of the same data set, and there might have been multiple times duplicacy of the same thing. Linear regression. So this is one of the important topic in a way, because now, I mean, I have discussed the sampling methods. We have discussed now that we are trying to make the data set into, I mean, we are trying to make the data set into two parts, training and testing, or maybe three parts when we are doing that validation also. So if those things are applied and the dataset has been converted into three, four different subparts, then we were trying to do the sample. Now, when the sampling has been complete, we want to train our model. Now, this is the first machine learning model that you will be implementing in your lab also. So linear regression, this is one of the first machine learning model that will help us to get the work done. So the basic idea is that, let's say that there is this data that we want to fit for a machine learning model, and we are trying to fit a straight line in this, because name of this model is linear regression. So we are trying to fit a straight line in a way that it is having the minimum loss means that it should be the best option that we are trying to implement, because this same straight line could have been uh, made with a different slope, let's say this. So this line 1 is good or line 2 is good? How will we make the decision? Anyone any idea about this? If we are trying to what we say, fit a straight line in this space with different red dots in the space, now which line is better?
Sir, the one who मतलब accommodate maximum red dots.
No,
Maybe
out of these L1 and L2, can you make a guess that which one will be better?
L1.
Okay, according to you, L1.
Sir.
Anyone for L2? So intuitively, some may say L1, some may say L2, but how to make a decision, that is the real problem. And the this problem can be solved by least square error fit method. Now we will discuss that what is this method, and based on that you can make the decision. Let's see. I will answer this question later on. I think that will be automatically answered also when once you see that what is being done in this method. So linear regression, in this machine learning and statistics, regression attempts to determine the strength and character of the relationship between one dependent variable and a series of other variables. Now the thing is simple. Again, you are trying to fit this function y equal to fx, but now your value has to be continuous. It is not a class, it is a continuous value. Let's say that you are trying to predict a housing price. uh, the, there might be n number of rooms, n number of floors, maybe uh, the area of the house. So multiple things might be there. So these are the independent variables. The this thing, other variables known as independent variables, these are all independent variables because they are individually contributing for decision making of the price of this house, right? So this price of this house is being determined based on these three factors. Let's say there were 5 rooms, there were 3 floors, and the area was maybe 150 square yards, something like that. Now the price might be around 1 cr, right? And this 1 cr might be exactly, let's say, 1.05 cr, something like that. Okay, and based on that, maybe second scenario comes. There are 7 rooms, 3 floors, and area is maybe 200 square yards. Then this price might go up to 2.50 cr. So you can see that these are continuous variables, 2.5, 1.05. There might be 0.57, 0.89. There might be multiple types of prices of houses. So these are all continuous values, real values. So this is basically the main idea behind linear regression, and we want to fit a straight line in a way that there is minimum error in this thing, minimum loss. We will look into this problem again. So this is housing price, right? House value prediction. And there are multiple things. Let's say plot size, number of bedrooms, covered area in yards, granite flooring, upgraded kitchen. So multiple factors are there. And price in lakhs is there. 70 lakhs, 1.4 crore, 2 crore, 60 lakhs, 2 crore, 60 lakhs. So multiple numbers are there. Now this is my output. So you can say that it is class, because in this case there are only limited numbers: 60, 70, uh, 200 and 140. There are only 4 types of prices. But if the list is long, you will see that there are multiple prices. Let's say 65 lakh is also available there, 60 lakh, 55 lakh. So in a way you can think it in terms of classes. But if classes are more than 1,000, let's say that this dataset was having 1 lakh rows, and in this 1 lakh rows, if this approach was being followed, let's say that number of classes were nearly 10,000, right? So obviously, instead of doing classification for 10,000 classes in this problem, you might want to consider it from regression point of view, that you want to predict a number which will be near something. Let's say the original price, the actual price prediction that was required was around 70 lakhs, and the prediction came out to be 68 lakhs. Now this is a better approach, because the gap will be checked, that there is a difference of 2 lakhs, and how much error is there. I mean, 2 lakh upon 70 lakh, and some percentage will be calculated. So 3% error was there, let's say, something like this was there. So it is better approach rather than doing classification, that yes, out of the 10,000 classes, in which class does it fall. So I just wanted to give you a basic idea about this problem. So this is a problem, and you want to solve it with simple linear regression. So simple linear regression, what does this mean? It is a linear regression model with a single explanatory variable. So what does this mean? It concerns two-dimensional sample points with one independent variable and one dependent variable. So in this, only two things are there. One is x variable, one is y variable. Based on only one value, you are going to give one output, rather than multiple inputs earlier. So this is not simple linear regression. This is different, but this is simple linear regression based on the this definition. There is only one independent variable, which is x, and one dependent variable, which is y. So this is how it goes. And then the adjective simple refers to that the outcome variable is related to single predictor. Okay, now, yeah, let's say that you want to fit a straight line in this space. Let's say that these are the x points. It is here, here, here. So you can see that there is gap between the original value and the straight line. So in a way, what you can do is you can, let's say, find the distance here. At all points, you can draw perpendiculars. It is lying on us in this line only. You can draw perpendiculars for each point on that straight line, and then you can add all the errors, right? So how much difference is there? I mean, what is the distance of that point from the straight line if we draw a perpendicular? That is what matters in this case. So what we will do is, let's say that we are trying to fit a straight line. Straight line, we studied in the small classes that y equal to mx plus c is a straight line. Similar to that, we have this equation y hat equal to b naught beta naught plus beta 1 x. So this is my m, this is my c, this is my y according to this equation, right? But in this case, y hat is being particularly used, and you have to remember this, that y hat means my predicted variable, and if we say normal standard y is being used, then it is the actual variable. I am telling you this thing because this will be used in the equations later on to find the error, original minus prediction. So this will be the error, and we might take the absolute value. So we will take different scenarios, that what kind of different ways are there to see the difference. So y minus y hat is the actual difference here in this case, right? Because this is the prediction. It is written here also, this is predicted value, and input variable x with the corresponding predicted value y can be given in the equation this, where beta 1 is the slope of the line, this m thing, same, right? And then beta naught is my y intercept, which was this c in our small classes. So y hat is the predicted value of the output for the particular value of input variable x. Now we want to see that what is the error or the cost, right? So the major goal of simple linear regression model is to fit a straight line that predict the output variable. Okay, we know. So now there might be a case, I told you that, let's say actual price of the house was 70, and prediction value came out to be 68, and there was this error of 2 lakhs, right? And this is the same thing written here, actual value equal to prediction plus error, right? So this has to be followed. Now you can calculate this residual error, if you want only error, then obviously you can do it by a minus b. Same thing is done here. So yi minus y hat I, so this is my error, and I mean there is nothing to be explained here. Now this error may be positive or negative, as it may predict the values greater or lesser. Obviously, I mean, if it is plus 2 here, there might be a case that the prediction is 72 and you have to do the minus to get the value of 70. So then the error will be minus 2. So the error might be positive or negative. So we will consider the square of each value just to bring them on the same scale. We will make it square. So if it was minus 2 or plus 2, it will be 4, right? So we will look at the error as a squared value. Now let's see, then what will be the total square error? It will be obviously epsilon square, and do the summation of all the points I equal to 1 to n, right? And because we were saying that we will be doing the square, so it will be this epsilon square, and obviously we will have to do it for each point of all the endpoints. So this will be the equation, and you can then substitute the values, that yes, epsilon was this my yi minus y hat I, right? And this thing, when I mean, you can put the y hat I formula also. It was beta naught plus beta 1 xi, something like that was there, right? We have seen this earlier. So this same thing has been substituted here, and it has led you here. So this is the equation of total square error. Okay, and now the mean of square error is called the cost or error function for this simple linear regression, which is denoted by j of beta naught beta 1 equal to 1 by n. And this, I mean, total square error was this. It was understandable that we are trying to do the summation of square of errors. Now because we have done this 1 by n also, so this is my mean. Now mean of square error is this formula, j of beta naught beta 1 equal to 1 by n summation yi minus beta naught minus beta 1 xi whole square. Now there are just many methods to optimize this function to find the line of best fit. Now because we know that this is the kind of error that we will be finding for that straight line that we are trying to fit. Now because we have to find the best fit line, because this was my first question on this slide, that L1 is good or L2 is good. Now based on this method we will try to make the decision that okay, we have got this, we have this mean or square error function, and we will try to get the value. And in what way we should do that, this is the straight, I mean this is the best fit. Is L1 good or L2 good? Now we have to do few things. Now because we have to do it for the best fit, we have to do a few things. Now the least square error method aims to find the beta naught hat, beta 1 hat for these two things, right? Now because we have to find it for the predictions also. I mean, this is kind of a first derivative. So this hat here means derivative, so we will be trying to solve it for beta naught hat and beta 1 hat by doing the first derivative. Can anyone tell me that when do we use this sign versus this derivative sign? Can anyone tell me that when do we do this partial derivative versus full derivative? How will you make this decision that you have to use this partial derivative sign here in this?
सर
Yes.
पार्शियल डेरिवेटिव सर तब करेंगे जब मतलब दो एक से ज़्यादा वेरिएबल होगा
Yes,
शायद।
yes, you are right. If we have more than one variable in the equation, then we will do partial derivative. And if it is only one single variable, then we will do full derivative. So that is why this symbol of partial derivative has been used here. Now we have to calculate the values beta naught hat and beta 1 hat for these two, with which the square error function is minimum. I mean, there are multiple steps and we have to see that what are the different steps. Now compute the partial derivative of this thing. So if you try to compute the partial derivative, you have to do it for this beta naught as well as beta 1. Twice you have to do it. And the formula will be, I mean, we will look into this now. So what we can do. So we have to, let's say that we have these two things, and we are trying to implement the values, and we want to find the value of beta naught hat and beta 1 hat. So you have to equate them to 0. Both of these things will be equated to 0, and after that you have to find the second partial derivative. You have to find the second order of it. So you will have to again do the derivative. So this was the first order, this is my second order, same thing is being done. And prove it to be minimum for beta naught hat and beta 1 hat. So let's see that what is being done. So total square error was this, right? And if we try to compute the partial derivative the first time, so uh, we will get, using this beta naught, my equation will become this, and using beta 1, my equation will become this. So if you have any doubt in this, you can ask, but otherwise, I mean, this has been calculated on my end, and this PPT has been, this is full proof that this mathematics is correct. But if you find that it is something different on your end, you can discuss with me. And then once these two things have been calculated, now we have the value of this delta j beta naught beta 1 upon delta beta naught. So my equation is this in this case, and in the beta 1 case it is this. Now if you want to calculate beta 1 and beta naught hat, both of these things, by equating them to 0, you will have to do it like this. So both the equations have to be equated to 0, and you can solve them. So this uh, n beta naught plus beta 1 hat, this summation of xi is equal to this. And in this case the equation looks like this. So it might look complex at this stage, but let's see that what happens next. So now when we solve this, you will find that in the end beta naught is equal to y bar minus beta 1 hat x bar. So y bar and x bar are the means of the original values, right? And I mean, this is how the equations are being solved. You can verify it on your end later on. So second thing is that you have to find the second partial derivative. You have to do again the derivative. So once you do it for the second derivative, you will get the values. The first value is 2, the second value for beta 1 is 2xi square. Now therefore both are positive. Now you cannot see a negative sign here, so the cost function continuously increases with respect to beta naught and beta 1 beyond this thing, but it attains the minimum value. So according to this, solving the equation and everything, we have seen that because the values are not negative, it means that it has been continuously increasing. And mathematically also it says that according to the algorithm we discussed earlier, we had to do these three things, and we once we have done this, we have seen that all of these things are I mean giving the right result, right? And now the linear function that binds the input variable x with the corresponding variable y hat, it has to be given in this equation. You have to fit everything here, so the final equation you can fit these values and you can get right. And let's do it on a example. So this is one variable, independent variable, and one dependent variable, right? So this is a very simple example, and these are the few things that you need to do. Now the data set gives average masses for women as a function of their height in a sample of American women of age 30 to 39. So this is the age group. Find a square line for average mass as function of height using least square error method, and predict the array mass. So this prediction will be done later on, but before that we have to find the equation of the line. So this is the data that we have been given. This is xi, this is yi, and you have to use your methods to get the final equation out of this. So before that you have to find these values xi square and xiyi, then only you can try to get the things, because we have seen earlier that these are the things required when when we are solving the equations. So beta 1 hat formula was this, and if you put all the values here, you will get beta 1 hat as 61.19 and beta naught hat as minus 38.88. So therefore the line will be this one. So this is the y equal to mx plus c, or maybe you can say y hat equal to beta naught plus beta 1 x equation. And for this x equal to 1.4, which was the part 2 question, when you put the values in this equation, you will get 46.78 weight of that lady that was asked here in the B part. So I mean, if you know the formulas and if you do the mathematics right, you will find this equation in very few steps, and you can do the prediction also. Now multiple linear regression, this is extension of that simple linear regression. I mean, the simple thing is that, I mean, the easiest way to remember is simple linear regression has only one variable x, but in multiple linear regression you have multiple, right? You have multiple x variables, multiple independent variables. Now because the variables are more, the equation might be a bit complex, but let's see that how does this multiple linear regression works. So multiple regression models describe how a single response variable y depends linearly on a number of value predictor variables. So I mean, we have discussed this earlier that for a house that there are multiple things to predict the housing price, or maybe if you want to predict the height of a child, it might be the case that you will have to consider the height of the mother, father, nutrition, environmental factors, how much he sleeps, how much he plays, how much he exercises. So there are multiple things that will be considered to check predict the height of a child also. So there are multiple things, right? And that's why it comes under multiple linear regression. The technique is same. I mean, the only thing that has been added here is that now you have all these things. You were earlier working with this y hat plus y hat equal to beta naught plus beta 1 x1, but now you have this beta 2 x2, beta 3 x3 up to beta k xk. You have multiple variables, right? You have up to xk predictor variables. The techniques are same. You will have to find the error. You have to I mean, the total error will be this thing, the same equation, but now with more variables. So if you solve it through the matrix method, you can you can do the prediction in a way that y minus x beta. So where I mean, these are all your matrices. Error is a matrix here, your actual value is a matrix here, beta value is a matrix here, and x is also matrix here. So all of them has been put into the matrix form so that our mathematics can be faster and more efficient. So according to the least square error method, we have to find the values of the matrix beta for which total square error is minimum. So j beta, this b- uh, this will be epsilon square. This is my square matrix. So when you solve this, it will be this error transpose into error, and once you do the mathematics, you will find that total square error is this equation. Now you can, I mean, solve this and you will get this in the end. Y transpose y minus 2y transpose x beta plus beta transpose x beta. So this is the final equation. You can solve the mathematics on your end and you will get the values. Now because these two is always equal with only one entry, so you can verify this statement on your end, but I hope this is self understandable. Now the square error function is minimized using the second derivative test. So it's not that you have to do only single derivative, you have to do the double derivative. So this is the first derivative, j beta upon delta beta, and once you solve this, you have to find the second derivative also. And by solving the second derivative, you have seen that it is positive here. You can verify, again I will say, you can solve this on your end, you can verify these results. This numerical we will do in the next class. Maybe you can take a screenshot and try to solve this numerical on your end. We will see, we will discuss the solution of this numerical in the next class.